Hello and welcome. This is the first video in chapter 23. This chapter is all about the electric field. Now the electric field is probably the most important concept in, well, almost all of this class actually. It's a central idea and it's a confusing one from the very beginning, so we want to make sure we can understand it. So the idea behind, sorry, just a minute. The idea behind, okay, sorry about that. The idea behind the electric field is that different shapes of charges create different shapes of electric fields. Now again, what does an electric field do? An electric field will exert a force on a charged object, and that force is equal to the strength of the charged object times the magnitude of the electric field that it's in. And the direction of that force points in the direction of the electric field if it's a positive charge, and it points against the direction of the field if it's a negative charge. So we have electric charges that come in all different shapes and sizes, and so each different shape of electric charge will give us a different formula for the electric field. And so in this chapter, what we're doing is we're developing a general formula to deal with finding the electric field of all sorts of these different shapes. Okay, the first and most important specific type of electric field is that of a point charge. The electric field of a point charge is electric field vectors that point radially outward, and they decrease the further away you go. If, like for instance, on the right hand side, if the electric charge is negative, then the electric field vectors point radially inward, actually. And this formula here, it does have the 1/4 pi epsilon naught, and as opposed to the capital K for the force constant in Coulomb's law, that is, we use 1/4 pi epsilon naught exclusively for the electric field. We don't use K because K is really just the constant in Coulomb's law, but epsilon naught is going to be more fundamental. And so a couple things that you notice here is that the electric field, it is a vector, and the direction of it points in the unit vector away or towards the object itself. So it points radially away, either 2 or 3 dimensionally. And the other part is that it's a 1/r² dependence. So the further out you go, the smaller the strength of the electric field is. So this is one way of visualizing it, a helpful way of visualizing it. Here's an interesting table with some typical values for the strength of the electric field. Again, the units of the electric field are newtons per coulomb. And so what drives electric current in a wire? Well, an electric field. So you have an electric field pushing the charges along. Right? You have the electric field that's created inside of a current carrying wire. It's pushing the electrons that are freely moving along. And so that electric field is the thing that's responsible for electric current. And you can see here those values for the electric field in SI units are pretty small, but since there's so much charge, you can still get a very large current from a very small electric field like this. As you can see, there's also different magnitudes of the electric field for different near the Earth's surface. When you rub objects together, right? I think one important value is in dry air, there is an electric field strength that's about 10 to the 6 volts per newtons per coulomb, and when it's around that, you get this new phenomena called the electrical breakdown of that material. So air, you will see like showers of sparks, and so those showers of sparks, they come because the electric field is just too strong. So basically every material has a maximum electric field that it can withstand before the material just breaks down and sparks just start to fly through the material to discharge it very rapidly. And then, inside of atoms gets bigger still. All right. So this is an important example. This is, for problem solving, this is an important slide because this says that electric field follows the principle of superposition. And that means that you can, if you have different source charges, then at a specific location, the electric field at that location is due to the vector sum of the electric field of both of them. So you will have to do these sorts of electric field vector problems. And here's a couple of examples. I'm not gonna, for this video, I'm not gonna go in detail as to what this, as to how to calculate this, but it's worth, you know, just sketching out what this looks like in this specific example. So in this example, what does the electric field look like at the bottom right corner for the left picture? Well, there's a positive charge on the upper right-hand corner. So there's an electric field that goes like that, right? There's also an electric field due to the charge on the bottom left-hand corner. It goes like that, okay? And there's also an electric field from the charge at the upper left-hand corner that points kind of like that. Notice how all these electric field vectors all point radially away or radially to the source charge that creates them. And so you have to use the vector sum of, you have to add these vectorially to get the net electric field. Okay, so what you'll actually measure, right, I think it turns out in this example that the result ends up being kind of something like this, right, for E net. Okay, so what you measure at this point in empty space, at this location of empty space on this lower right-hand corner, what you measure for the electric field is the resulting magnitude of all three of them when added vectorially. And do the same thing for the other ones. This gives you good practice with vectors and components, kind of a review from Physics 1. So the point charge, right? The point charge is the first basic important example of an electric field. The next example would be that of an electric dipole. And there's several different important topics related to this one. First of all, what is an electric dipole? Well, an electric dipole itself is defined in its most basic form. It's defined as you just take a positive charge and stick it next to a negative charge. And as long as these 2 point charges are fixed in position relative to one another, like imagine like a small rod connecting them, right? Then every point around them will have an electric field that points radially away from the positive, and also an electric field vector that points radially towards the negative. So say you're out here, right? What would be the electric field? Well, there'd be there'd be an electric field that points radially away from the positive one, and there'd be one that points radially towards the negative one. And so you'd have to do vector addition with, you know, the parallelogram to get like an E net. Okay, so that vector in the middle, that would be the net electric field. That would be what you would actually measure due to the electric field of both of them. So by itself, it doesn't seem very interesting, but it turns out that most molecules can be modeled as an electric dipole. So we have a water molecule right here. A water molecule right here can be modeled very well as an electric dipole, right? So if you have an oxygen atom with, you know, pretty much have this covalent bond between the hydrogen atoms and the oxygen atom, then you kind of have a sort of an ionic or a distribution of charge here where you pretty much have a positive charge of magnitude 2e, and then a negative charge at the bottom here of magnitude minus 2e, right? And then some separation, right? If you look up the old values of the bond distance between water molecules, you'll find it's about an angstrom. And so So basically a water molecule acts electronically, can be modeled electronically as a pair of charges that are separated by a small distance. Okay, and since the concept of the dipole is so important, we actually characterize a dipole by a vector, and that vector is called the electric dipole moment. So it has a magnitude. The magnitude of this vector is defined as the magnitude of the charge times their distance, Q times S. So that means that the dipole moment has units of coulombs per meter. And the direction of the electric dipole moment is always pointing from the negative charge to the positive charge. So if we go back to this water molecule here, we'll go on this left-hand side, got the oxygen atom, and then these hydrogen atoms. If we go back to those average sizes, we'll see that this is what the dipole moment looks like. Okay, the oxygen, the water molecule has an electric dipole moment that points like that from kind of the negative to the positive. So that's how an electric dipole will, that's how well, we'll see later in the chapter how electric dipoles respond to other electric fields. It turns out that electric dipoles can rotate in an electric field. Okay, so pretty much any molecule that's not nonpolar, right? Your nonpolar molecules being your standard diatomic molecules and maybe a couple of other specific geometries of like maybe carbon rings or something. Pretty much any molecule is going to be nonpolar. Or sorry, pretty much any molecule will be polar. So pretty much any molecule will have an electric dipole moment. And I'm sure you can find tables somewhere of the magnitudes of those dipole moments. So moving on to the next thing here. Let's see. Just a minute, I'm having some technical difficulties. Okay, back moving. So when it comes to calculating the electric field, really, of the dipole, you can only really do it in a few cases. There's a general formula, but it's a lot harder to derive. And so this little picture describes the this little picture describes how you would find the direction of the electric field in two specific spots of an electric dipole. The first one being the electric field on axis of the dipole. So on the axis that is you know, connecting the line between the positive and negative charge, right? In both cases, if you're either above the positive charge or below the negative charge, the axis or the dipole, or sorry, the electric field actually points upward. It doesn't point downward when you're on the negative, below the negative. And then with the other picture is the bisecting plane. So if you're on the bisecting plane of the electric dipole, you can do the superposition to see that the electric field always points downward against the direction of the dipole moment. And those two directions are summarized in a formula, in the two formulas for the electric fields of these dipoles. In lecture, in the online class, we derived the top formula, and you can do the same thing for the bottom formula. But notice what we have. We have the electric field in terms of the dipole moment. Okay, the dipole moment points up from positive to negative. And so on axis, when you make this assumption that you're measuring the electric field far away from the dipole, so that means the distance that you're measuring it to is big compared to the separation of the charges, you find that the electric field is in the same direction as the dipole moment, and it drops off like 1 over the distance cubed, not 1 over the distance squared. And for the bisecting part, you have the opposite effect. It's negative, so it points against the direction of the dipole moment, still dropping off as 1 over z cubed, or 1 over r cubed. If folks are interested, this happens to be a general formula to deal with the electric field of a dipole. You have to be kind of careful here with this notation. This is taken from an advanced textbook. That r hat is still the vector that points radially away, but theta hat is a vector that points perpendicular to r hat. And you just have to be careful with what that actually means. But if you look at this, turns out that if you put the right angles in here, you can recover both of these formulas. So that's a brief intro to calculating the electric fields of different discrete charge distributions. Okay, ultimately, the electric fields of all discrete charge distributions, that means collections of point particles, can be derived from the general definition of the electric field of a point charge, this thing right here. Okay, this thing governs the electric field of all sorts of different collections of point charges. In the next video, we'll talk about how the electric field of continuous charge distributions, that is, solid objects that aren't point charges, how those can be calculated. So until then, thanks for your time. Appreciate your watching this video.